workshop. Maybe this is the second or third time for me to give a lecture in this room. So I'm very happy to come back here. And today I'd like to talk about this title. And recently, you know very well that Pairings is a very, very powerful tool in cryptography. So firstly, let me consider why the pairings are so powerful. So it means that pairing provides us mathematically richer structure than just cyclic groups. Okay, so this is a typical algebraic structure which are used in cryptography in many applications. But this is mathematically has a very simple structure, a genus cell structure, like a circle. And pairing uses a richer mathematical structure than just a genus cell cyclic, but a genus 1 structure. So it's a kind of a torus. So the structure is some product of two cyclic groups. And such a structure can be can provide us pairing operations. Okay, so it means also such a mathematically richer structure very useful in cryptography. So how the pairing are used in cryptography? So just a genus cell structure provides us one-wayness and commutativity and homomorphism. But pairing provides us additional algebraic structure as well as these structures, these properties. So additional structure, additional properties, bilinearity, as you know. So this is very good in many applications. So the target in my talk is to consider how to construct additionally richer structure from pairing groups. So then the starting point is pairing groups, and maybe we can construct a richer structure based on pairing groups. So let me remind you the notation of pairing groups by this. So G1, G2, GT are three groups with prime order Q. And now I use additive form expression for G1, G2, and multiplicative form expression for GT. It's a traditional mathematics in elliptic curves. And pairing E is defined over G1 times G2 to GT. And it has two properties, non-degenerate and bilinearity. So now, this is a notation of pairing groups in my talk. So the most natural way to make richer algebraic structures from pairing groups is direct product of pairing groups. Direct product is just a couple of group element. Okay, for example, now we consider the n direct product of groups, and V is over G1 and V star is over G2, and direct product means element of X is element X in V is expressed by just a tuple of a group element of this group. And similarly, the element of this space is, okay, maybe I use better to use. Each element is from this group, and it's just a tuple of an element of group. And this is just a tuple, but this has a mathematical structure. Okay. This tuple, this direct product constitutes a n-dimensional vector space. So then, firstly, we can define a vector addition like this. So this is an element of a V, and this is an element of a V. Okay, both are same. Two elements from a same group, same space. And addition is defined as element-wise addition. So then this is addition for the group addition. Then this is also n tuple of group 1. It means this is also an element in this space. So then we can define a definition of this space, and similarly we can also define addition for V star. And next we can introduce scalar multiplication. It is also a very natural way of multiplication like this. So element-wise scalar multiplication is applied for the scalar multiplication of space element. Okay, so then C times X is expressed by this way, is C times first element and C times second element and the other C times last element and the tuple. So this is also an element of V. So then, and similarly we can define a scalar multiplication for V star. So by this definition, this space constitutes a vector space. Okay, so vector space V and V star are vector spaces. Okay. Next step is so vector space. Has some basis. So n-dimensional vector space has n basis with n elements. So the canonical, typical basis is this form of a canonical basis. So then A1 is G1, 0, 0, 0, and H is this form, the AN is this form. Then this is typical basis for this space, and this is also a typical basis for this space, and we call this canonical basis. Okay, and so then we can express any element by the coefficient vector over a canonical basis. So then this is an element, so just an n tuple of a group element can be expressed by the linear combination of canonical basis, and the coefficient vector over canonical basis is expressed by this and this vector. Okay, so then it's a very natural expression of an element in a vector space, and similarly we can do like this. Okay, and the canonical basis itself can be expressed by this form coefficient vector expression. Okay. So next, we can introduce duality of the vector spaces. It's also a very standard way of definition of duality in vector spaces. So firstly, we introduce inner product between between V and V star. So then element in V is expressed by this way, and Y is expressed this way. Then the inner product of X and Y is defined by the inner product of X vector and Y vector, which is in FQ. Okay? And then we can define a duality. So now, by using the inner product, we can define a linear map by Y from V to FQ, like this, by using the inner product. Then we can define that we know that V star is a dual space of in a standard way in the linear vector spaces. Okay? And given X and Y, it is not easy to compute inner product because to compute X vector and Y vector given X and Y, we have to compute a discrete logarithm. Okay? So it is not easy, but to compute the pairing, another value is easier. So now we introduce a pairing between V and V star. So pairing is originally defined over a group. So now first starting point is pairing groups. So then pairing over G1 and G2 are already defined. Then using such element-wise, primitive-wise pairing for pairing operation over V and V star. So then pairing of element in V and element in V star can be defined by this way. So firstly, each element is expressed like this, and so then to define a pairing between X and Y, we calculate pairing component-wise. Then we multiply them. The product of component-wise pairing is a definition of pairing. So then now I have used the same notation E here, but originally E is defined of group pairing, but now I abuse. Okay. Anyway, so then by this definition, it is by the bilinearity. This is equivalent to this value. It means this is a GT2 inner product of X vector and Y vector. It means okay, this is a GT to the power of inner product of X. So that means pairing of X and Y is GT to the inner product of X and XY. It means so it is interactable to compute inner product directly, but this is efficiently computed. It means G2 inner product of XY can be efficiently computed. Okay. So okay. So then we introduce duality, and we can confirm that A and A star dual orthonormal basis of V and V star, because the inner product of AI and AJ star, and here is a Kronecker delta Ij. Means if I and J is equivalent, then the value is 1. And if not equivalent, then value is 0. And so then the pairing of AI and AJ star is GT to the Kronecker delta. It means if I equal J, then it is a GT. And if I is not J, this value is 1. Okay. So next step in a concept is that to introduce base change. So already we know that's a canonical basis, but if we can allow freedom to select a basis, so any randomly selected independent n values can be a basis of the space. So then, so such a random basis can be obtained from the some linear transformation from canonical basis. Okay, first we generate a random matrix, n times n matrix from here, and then by using the, it means it's a linear transformation of V, and by using this linear transformation, we can transform a canonical basis to a random basis. Okay, like this. Okay, like this. So this is a canonical basis, and apply a random linear transformation. Then we can obtain a random basis. Okay, so similarly, we can introduce another basis for dual space V star. But here, the linear transformation is not just random, but this is related to this transformation in a vector space V. So this is adjacent matrix. It's a transpose or inverse of transpose X. Okay. Then we apply this linear transformation for canonical basis. So then this canonical basis is transformed to another basis B star. So then, as I mentioned that A and A star are orthonormal basis. By using this type of transformation X and X inverse, B and B star again become orthonormal. Okay. So this is a very nice property for it means pairing of a BI. Okay, BI and BJ star is again Kronecker delta. It means pairing of a BI BJ star is GT to Kronecker delta. So okay, this is essentially, this property is essentially used in many cryptographic applications. Pardon?
The B matrix, which we are
B matrix?
yes, sir. B and
B.
star.
It's a each element is a element of a V.
Yes, sir. So, because we have got A matrices which is in canonical form.
Yes.
And we are transforming it
Yeah.
into
Yeah. So then, by this way, so the basis of A So A1 to the AN is transformed to a B1 to the BN.
Which is also canonical.
Not canonical. Canonical means only we call A and A star is a canonical basis, and we call this B and B star is just a basis, not a canonical. But B and B star has a very nice property that they are dual orthonormal basis, so satisfy this property. Okay. Okay, so then now, so we started from a canonical basis, and there are dual orthonormal basis of these dual spaces, like this, and we apply a base change by using a random linear transformation. Then we obtain another basis, but still preserve the nice property of the orthonormal basis of two spaces. Okay. Okay. So then, Then so now, if we express element of a V via over this basis, so then before we consider some expression over a canonical basis vector. Okay. So any element is expressed as over a canonical basis, but now we express same element by another basis. Okay, so then we got another expression of the same element, of course. Then it is expressed by the expector over this basis. And this element in, maybe it's a V star, I'm sorry, V star. And it is also expressed by a vector over V star. And then, due to the property of the orthonormal basis, the pairing of x, y is, it's this expression by the definition. And, but due to this orthonormal property of the, so it means if I and j are equivalent, not equivalent, then just pairing value is just 1. And if I and j is equivalent, then it is gt. It means gt to xi and xy, gt to some xi times yi is here. Then this value is becomes this value, and so then finally we got the pairing value is gt to the inner product of x vector and y vector, and x vector y vector is vector expression over basis b and over b star. Okay, so by this, it's a very nice property in many cryptographic applications. Okay, I will explain later. And so now, for example, this value is published. This value is published. Then it is not easy to compute this value, because even these values are given. It's not easy to compute capital X one linear transformation from A to B. And but if linear transformation from A to B is given, of course, as I mentioned, that the transformation from A star to B star can be computed by using inverse of X. Then it is easy. So it's a trapdoor. And so we often use some special cases of self-duality. So if we use a symmetric pairing group, so here is a G1 equal to G2, then pairing is defined like this. Then the vector space of V is equivalent to V star by this. And so then, so since V is equivalent to V star, then only one canonical basis for both. And then we apply a linear transformation. Then we got a B and B star like this. Okay. So then X is applied from A to B, and X invert is applied to A to B star. Then this property is satisfied. And again, it is hard from a B and A to compute B star, but it is easy by using trapdoor capital X. So now, so we introduce from just a tuple of groups, and we introduce in a vector space structure and inner product and dual spaces and that vector base transformation, etc. Then we can abstract this concept as dual pairing vector spaces, DPVS. So DPVS is a tuple of Q, V, V star, GT, A star, and Q is prime. V and V star are m-dimensional vector spaces of FQ, and GT is a cyclic group with order Q, and A and A star are canonical bases, and the efficient algorithms of E phi ij and phi ij star such that there are three properties. The first one is bilinear pairings. So then E means bilinear pairings over V times V star to GT, and it's a property of the bilinearity. Okay, and non-degenerate property. And so second one is dual orthonormal property for canonical basis here. And the third property is phi ij and phi ij star. This is called a distortion map, which is the endomorphism of V such that phi ij aj equal ai, and phi ij ak is a 0 if k is not j. And also similarly define phi ij star. Okay, and okay, then we call this a distortion map. So the typical example of distortion maps of direct product of a construction that if X is this form, okay, it's a tuple of n element, and then if we apply a distortion map over here, then this value is located in j's ith location. So j's value is located in the ith position, and the other elements are 0. This is a very simple operation. This is a typical example of distortion maps. Okay, So how to construct such a concept, dual pairing vector spaces? So the first one is just I introduced you that direct product of pairing groups. So it's maybe you can confirm that this satisfies the property of the dual pairing vector spaces. And another construction is a Jacobian of supersingular hyperelliptic curves. This is a bit more complicated than just a direct product pairing groups. But in many cryptographic applications, I think this is much better than this construction. This construction has a lot of restriction in implementation, and this is much easier to implement. So then, after that, I assume this construction for this space. Okay. Then I'd like to, so I've already introduced a concept of vector pairing, dual pairing vector spaces. And to apply this concept to cryptography, we have to introduce some suitable some interactive problems, hard problems. So then I introduce 3 problems in my talk. The first one is vector decomposition problem. Second one is decisional version of this problem. And third one is another decisional problem, decisional subspace problem. Okay. So vector decomposition problem is defined like this. Firstly, the two spaces, V and V star, and canonical basis, and random basis of V is a given. Okay. Then now X is a secret from here, from public values, some kind of trapdoor. And so then V is just a linear combination of over this basis. Okay? And the problem is that to decompose this part from a whole value. Okay? So the value is expressed by the n tuple. It's an element of V. It means n tuple of a group element. So then the given the subset of bases, for example B1 to Bn2, then the problem to calculate this value. Okay, it means decompose this part from a whole part. Okay, maybe it looks difficult because it's just n tuples, and to decompose from this to this value, to compute some discrete logarithm, etc. So then, this is a vector decomposition problem. Okay, this looks hard. But if we consider this problem in a very special case of a very special basis, this problem is easy. So what is the case? So the original, this problem is defined over random basis. But if we define this problem over canonical basis, okay, then it means this value is some linear combination over this basis, and it's a V1 times A1, da, da, da. Then, in a canonical basis, this value is expressed by this way. So, it's also any tuple of a group element, but V1 is a V1 times G1, and V2 is a V2 times, and then, so this coefficient is only over this values. Okay, so then if we apply this problem, this question to decompose from this value, from here to this value part is trivial because I just extract this one. Okay, then this problem is very trivial. So the difference that the previous original one is defined over canonical basis. So then these linear coefficients so apply summation of these values. So then it is hard to extract, but in a canonical basis, this part is easily decomposable. Okay, so then by using this property, we can compute this problem by using a trapdoor. Okay, so now this is the original vector decomposition problem of a random vector, random basis. So should be difficult but if we give the trapdoor X, then by using the trapdoor X, then by using this algorithm, so then it is easy. We can decompose this part. Okay, so this is a trapdoor vector decomposition problem. Then move to a decisional problem of this problem.
Excuse me.
Yeah.
In the canonical base case,
Yeah.
why it is?
Canonical basis. Okay. Here.
Yeah.
Yeah. It's even if there is no trapdoor X, but everything is no random basis, only a defined over canonical basis, then this is easy. Trivially, only this is extracted by this way, and decomposition means just extract this part and adding 0. Yeah. So this is a trivial case, but not for this general random basis. But if we know the trapdoor, if we know the transformation from a canonical basis to this random base, then we can decompose this part. Okay. Okay. So then next we move to a decisional problem of this vector decomposition problem. Okay, and this is a very natural decisional problem. So then the part is the same as a computational vector decomposition problem. And here, this correct solution is given or another random element over same space, same subspace is given. Then, so the decision problem is to distinguish the pair of the VU and pair of VU prime. Okay, so then the advantage of this problem assumption is that the adversary outputs one probability of adversary at one given VU and VU dash, VU prime, then the assumption means that the probability is almost same. Okay. So next we will introduce another decisional problem, and this problem is more natural as a decisional problem. Okay. So this part is same as a vector decomposition problem. Okay, it means V is uniformly selected from this space. Okay, and the coefficient of V1 to Vn1 are randomly selected, uniformly selected. So then this is uniformly selected, and we also sample another element. In this case, this is a linear combination of basis, a subset of basis B1 through Bn2. It means this value is uniformly selected from this subspace. Okay, so then it's uniformly selected from a whole space, and this selected from a subspace. Then the problem is to distinguish two cases. Okay, so then the assumption, DSP assumption means that so then the adversary to distinguish two cases are negligible. Okay. Okay, so this is maybe this type of assumptions are very some similar to the traditionally employed in cryptography, such as decisional, some subgroup assumption, something, okay, some quadratic gradient assumption, etc. Okay, so then now we observe the relation with DDH problem and DLIN problems. So, okay, decisional S linear assumption is defined like this. Now G and G1, the GS selected from a group, pairing group G, and S1, X1 through XS plus 1 are selected from FQ, and given G to GS, it's hard to distinguish the two cases. The first element is so then X1 times G1 and the XS times GS, and another random element times G. Okay, so it's just a random element of a group. But this case, V prime is the different in this part. So this is a scalar, is a summation of this coefficient. Okay, scalar multiplication. So then, okay. So this is a general case of a DDH problem. DDH problem in this S equal in one case. So if S equal 1, then G1 and X1 times G1 and X2G and G1 and this is okay, X1, this is just X1G. Okay, so then this is so decisional one linear assumption is a DDH assumption. Okay. Then we consider this like this. We rephrase like this. So G1 through GS element of G, then expressed by the kappa 1G to the kappa SG. Then we define some element of the vector space. So in this case is S plus 1 dimensional vector space, as I mentioned, kind of in the element of a DP dual pairing vector spaces. So then G1 is expressed by this tuple. So then if we use a canonical basis A1 to AS plus 1, then it's expressed by kappa 1 A1 plus AS plus 1. And similarly, B2 is defined as this form, and BS is defined this form, and BS plus 1 is defined like this. So then this is expressed by this way. So then this is a kind of a basis of a vector space, and this is a canonical basis, and this is transformed from a canonical basis by this matrix, this companion form of a companion matrix. Okay, and so how to define this decisional linear assumptions is rephrased by this. This is expressed by the so this is expressed by this way. Okay, because okay, anyway. So then it means x1 through xs plus, again, this is expressed by this way. So then it is xs plus 1 prime is also independent from x1 to xs. Then it means this value is uniformly selected from the whole space. And in this case, Vista case is due to this property, this element. So this is expressed by this way. Okay, then it is uniformly selected from subspace. Okay, this is a whole space. This is it's a S plus 1 dimensional whole space, but a S dimensional subspace. Okay, so then the problem of decisional S-linear assumption means how to distinguish element from whole space and element selected from subspace. So it means this is a very special case of this DSP, decisional subspace problem again. So then decisional DSP problem is that how to distinguish two cases. V is selected from a whole space and V prime is selected from a subspace. So then this is exactly same form as so then in our definition of a DSP, this matrix is more random, just a random matrix. But if we restrict this transformation, this is just a given assumption. Okay. Now we can, so we mentioned that's a trapdoor for a vector decomposition problem, but we so then anyway, so we already mentioned that's a trapdoor for a vector decomposition problem by using a matrix X, and by using B star without using not directly from X, but by just using B star, we can also compute or distinguish, solve the decisional problem, DSP problem. For example, if T star is an element of this subspace, then to distinguish V and V star, this type of element is effectively used to distinguish by using a pairing. By if we got a T star, by if we apply a pairing, V and T star is not one with high probability, but for a V star, this is always one. So then we can distinguish with a very high probability by using this value. Okay, so now in our framework, we can, there is a very rich structure for trapdoors. For example, in just discrete logarithms, the trapdoor is very limited, and even for RSA, etc., very limited. But here, this structure provides us a very rich trapdoor. So now, A and B are public parameters. And then, as I mentioned, that it is hard to extract computer transformation from a transformation matrix X from A to B. And but as mentioned, if we got this trapdoor, it is easy to solve a vector decomposition problem over V. So it is this is a kind of top-level trapdoor, very powerful trapdoor to solve almost all hard problem over defined B basis B. And so if we got X, it is of course easy. So by giving X, we can calculate X invert. Then if we got X invert, we can calculate B star from A. So then it is easy, but of course it is hard from here, and also hard. Given B star, A and B and B star, it is hard to compute capital X, maybe without computing a discrete logarithm. Okay, and but I mentioned that if we got a B star, we can solve any DSP, decisional subspace problem, etc. This is a very powerful trapdoor to solve many decision problems over these parameters. And again, we can extract some value in the space spanned by the B star. And of course, it is hard from the public parameters. And also, even if I got some information about some space of this basis, but it is hard to recover the whole B star. And but still, this is effective to solve some specific DS problems. As I mentioned, so if we got some element inside the B spanner B star, still such a single element is still very effective to solve a DSP problem. Okay, so then anyway, we have, and from B star there are many varieties of trapdoors in the space. So then very rich structure for trapdoors in this concept. Okay, so it means we got a lot of cryptographic tricks by using this rich structure of trapdoors. Then maybe it's a good timing to have a break. Then after break, I will explain how this type of trapdoors apply to some cryptographic schemes. Okay, so okay, have a break, maybe 10 minutes. Okay.
Not break.
Ah, okay, some okay.